new technologies, sober consumption, going to another planet. There are many ideas to try to solve climate change. Yet, the problem is still there, relentless, every day, increasingly threatening. Have we really explored all the possible ways to escape climate change? Elon Musk offers $100 million for the best carbon capture technology. But don't we already have that technology right here, in front of us? Trees. Human being has never stopped innovating, working to push the boundaries of technology and finally find a system to capture carbon. How ironic. Trees have always done exactly that job for free, and we despise them, destroy them, ignore them. So in this video, we're going to pay tribute to them. We are 3 students from the Master in Sustainable Management and Technology at E4S and have chosen to study climate sustainability for our final semester project in data science. The main research paper of our study is entitled Is a Trillion Trees Enough? And was written by Cédric Ménage from the Universal Research Center and Michalis Vlachos from the University of Lausanne. The objective is to study the impact of planting 1 trillion trees in the Sahara Desert on global temperature and the contribution of this initiative to the Paris Agreement, which requires staying below temperature increase of 1.5 degrees Celsius. They developed a simple data-driven model to predict the global average temperature in diverse scenarios to better understand the outcome of human interventions. So we too asked ourselves the question, can 1 trillion trees save the world? We started by replicating the code from the original paper. Indeed, the code was presented in Python, and we used Wolfram to reformulate it. The reason for this change is Wolfram's extensive data visualization tools and its interest in presenting results. After we finished transcribing the code, we created a new model to include albedo and the water cycle. The effect of trees on temperature is a complex process. Trees are not only carbon absorbers, they have an important role on albedo and the water cycle. So we will deal with these elements and present our model after introducing the replication of the initial code. So let's now focus on the paper and its code. For the purpose of realism, the paper focuses on several scenarios. 2 metrics are considered that affect the evolution of CO2 concentration and temperature over time. First, there are assumptions directly about the trees themselves, divided into 3 cases. The case where there are no trees, the case where they capture 42 gigatons of CO2, and the case where they capture 107 gigatons. On the other hand, the behavior of the society is included by looking at different scenarios. It can continue business as usual, so continue emitting CO2, or reduce its emissions to 69 to 10% or even reach the net zero. All these elements are already included in the paper and are fully justified. We have, of course, replicated them, but our aim here is to take this model even further. As mentioned earlier, there are additional factors that need to be included. Okay, so here is the code that we replicated first. So, of course, you'll have the code at your disposal, so I invite you to consult it. But anyway, we are still going to have a quick look around it. So first of all, we imported the datasets. So that was the, let's say, easiest part, even if we had to manipulate it a bit to work on it later on. So basically that was only about the dataset and so on. Here is the polynomial regression. So basically we decided to not include the linear one because it was not that useful for the rest of the work we did after that. Basically what you can find here is exactly the same that you have in the Python notebook. Here are all the scenarios, so as well, the same as in the Python notebook with a lot of code and so on. And finally, what we decided to do is a just play with it section. What does it mean? Basically, it means that here we decided to put all the work that has been done in Python in a manipulate widget that you can find on Wolfram. So basically here you can select the sequestration by trees and the decrease by society, and you can plot the related graph. And you can run a lot of graphs just to compare the situation. So for example, let's put this one, and here you can see that they are different. And they both refer to different things in the Python notebook. So what did we want to change and why? One of the biggest challenges we had in extending the modeling was to answer the question how to integrate albedo and the water cycle into the code model. We were lucky enough to talk to Ellen Angot, one of our Science of Climate Change course assistants, who guided us through a number of literature articles which allowed us to find the following elements to model each aspect. For albedo, we used the scientific equation and made many calculations beforehand. Indeed, on Cedric's advice, we established our hypothesis on the albedo thanks to scientific formulas in order to gain in precision. For the modeling of the water cycle, we use clouds as a basis. They actually include a multitude of effects such as albedo and especially the water cycle. So we took into account the number of clouds that a trillion trees would create. Finally, regarding these trillion trees, we tried to understand what kind of trees and where we will plant them. We came to the conclusion that we will use an Acacia tortilis because it is a type of tree that stands out the most in desert plantings and absorbs the most carbon in these conditions. This tree requires about 50 meters squares, and according to our calculation, to plant a trillion of them, we will have to occupy all the desert in the world, not just the Sahara. First extension of our work compared to the initial goal. For the calculation of the albedo effect and the water cycle, we reasoned as follows. Firstly, changing the light surface of the desert to a greener, darker surface of trees will change the albedo and have an impact on global warming. Secondly, regarding the water cycle, we have done a lot of research and it is a very complex process. We found an article that explained that cloud cover is denser over forests. We then decided to include this in our albedo calculation. We know that this method has many limitations, but we thought it would be interesting to include this point in our analysis. First of all, you can see the different values used in our calculations. Following the information from the article mentioned above, we deduced that the cloud cover is about 85% over forests and only 20% over deserts. We show here also the different albedo values used in our calculations. Before estimating the temperature, we'll look for the average solar insolation received on the Earth. To do this, we first calculated the flux density received by Earth with the following formula. We find a result of about 1,369. We then divided this result by 4 to find the average solar insolation received on Earth, a value we will use later in our calculation. First of all, we will calculate what the temperature will be if the Earth was completely covered by desert, and therefore 20% covered by clouds. We started by finding the amount of radiation reflected by the desert surface. To do this, we multiplied the albedo of the desert by the total amount of radiation that reaches the Earth. We did the same for the clouds. Then we calculated the average amounts of reflected rays by taking the ratios defined before, 20% clouds and 80% desert. We deduced the numbers of rays absorbed by the Earth, which is simply the total quantity minus the reflected quantity. We then calculated the temperature of the Earth according to the number of absorbed rays found just before. We then transposed in degrees Celsius. Then, we repeated the same process, but this time with the land completely covered by forest, and therefore 85% covered by clouds. Finally, we will calculate the difference in temperature between a planet covered with desert or forest. To do this, we simply subtracted the temperatures found in the two previous cases. It is this temperature difference that we then used in our code. We will then apply it to the desired surface, which in this case is the surface of the deserts replaced by the planting of 1 trillion trees. Indeed, our delta represents the difference in the case where the whole surface of the planet was changed, and we must now apply this difference only to the desired surface. Using this method, We can even find the temperature difference for a single tree, which will allow us to have graphs that change according to the numbers of trees planted. Okay, so here we are. This is the final product of the code that we've done. So basically, we created the same thing as before, so a just play with it section. So basically, we just wanted to show different graphs with different settings of number of trees and decrease by society and compare them together. So we have the different impact of albedo and water cycle. So the interest to do that was, again, to show if there is a concrete difference if we take these two new things in account. So basically, we are going to conclude just after. I don't want to spoil you, but yeah, we just proceeded like the same way for replicating the Python code and doing our own to see if there are significant effects. As a conclusion, we can say that in general this work has told us several things. Whatever happens, the situation is dramatic. Humanity is heading for a wall but does not realize it. The madness of technology leads humanity to forget sobriety and nature, which is so useful. However, even considering trees with a water cycle and albedo, we realized that the scenarios are still alarming. Of course, if we rely them, then we are saved. But how realistic is the modeling and application? For the future, we recommend integrating water vapor into the model and studying in more detail which aspect of trees allow for carbon capture and under what conditions related to cloud creation. Of course, this could be the subject of a master thesis, but with this work we hope to have provided new ideas for hypotheses for research on the subject and to have contributed in our own small way to providing research to combat the warming of our common home, Earth.